Okay, guys, good morning to everybody. We do have a handout. Stereochemistry, this is the outline for stereochemistry. I sent you another one by email. Sorry, this is 2 stacks. Just get one. We're looking at halohydrons. Halohydrons. Any questions about lab today? Let's look at halohydrons. Reacting with halogen and water, typically bromine or chlorine, most common. You can do iodine here. Typically we won't do anything with fluorine. Okay, we have an alkene, we have halogen and water. What type of product? Halohydrin. You got to know that. Something for a note card right there. Let's see, we have an alkene. We know halohydrin, we're going to have halogen on one carbon and what on the other carbon? OH. Okay, so this is the starting point. These are the things you have to organize in your mind. All right, so an OH on one carbon, chlorine on the other. That's it. Which carbon is the OH going to be on, left or right? Be on the left, correct? Everybody see that? No. These are the types of questions that you have to answer to then show the correct product. The correct product is boom, 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 boom. Boom, boom. We're going to have chlorine here, and we're going to have OH here. That should be the product, right? In terms of stereochemistry, that's not it. There's no stereochemistry here. This is chiral. We'll just label that with a star. We'll talk about that later. All right? That's your product, right? That came from mechanism, but I can do mechanism in my head. I would suggest you do it on your paper. So you get good at it, then you can do it in your head. What's the only intermediate here? Well, there's actually more than one intermediate. What's the primary intermediate? One that we have a name for. Right, the chloronium ion, right? Yeah, chloronium ion. I'm going to do it without any stereochemistry. Right, the chloronium ion. Yeah? Could you get to this point? Mechanism, we've covered it. You'll have to show mechanism for your reactions on test. But I'm not going to repeat what we've already done before. You should be repeating it over and over, and then you should say, yeah, I can do that. And then water attacks, right? Where's water going to attack, left or right? What's the same place we'd form a cation? It's not a cation because it's back bonded concertedly. Really didn't form a cation. This is the first intermediate. Then the water comes in, attacks over here, right? That's more substituted. So this guy's going to pull, you're going to get more partial positive here. These electrons attack here and kick that off, right? We can eventually get the final product. After, we have to lose an H from the oxygen. What takes the H? There's another Cl minus floating around here, right? Okay. Cl minus can take the H. We also get HCl as a byproduct. Typically, though, you're asked to show the major organic product. All right? Questions about this outcome? How do we do on it? Any questions about it? Yes?
Is that star next to the C that's where the Cl is bonded, is that showing that it's stereochemical?
It is. That's a chiral carbon, and thus it has sort of, like my hands, a left and a right version. We could show one of these bonds forward and then show it with its back. That means it's racemic. We'll talk more about that. That's an indicator. Where this is not. That's not chiral. And so over there you can show it forward or back. It doesn't matter. We'll talk more about it. The bromine. Well, that's easy. Yeah? I mean, boom, 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 boom. But I implore you, you've got to use your mechanism to get the product. Although Br2, I mean, it's just Br here and Br here. Right? It's one of the easiest reactions ever. You don't even have any regiochemistry to predict there. Unless you want to put this Br here and that Br there. No? No different, right? Okay? That is chiral. This is not. We'll learn when we will have to consider stereochemistry. How about down here though? ICL. ICL. We saw that before. Which halogen is electrophilic? Which halogen is the alkene going to attack? Iodine, right? Okay, partial plus. Let's do this more mechanistically. We could have did these the same mechanism. Pi bond attacks iodine. Where are we going to leave cation? Top or bottom? Bottom, right? So this comes up here, attacks iodine, kicks off the chlorine. This is going to give bond to iodine. Down here we have an ethyl, and we have a carbocation down here. Okay. I showed this, but is this actually going to form, or is something else going to happen at the same exact time? Iodine is going to back bond, right? Importantly though, before we do that, this is tetrahedral now. This carbon's tetrahedral. There is an H there, right? The carbon's got 4 bonds, tetrahedral. 2 in the plane, 1 forward, 1 back. We now need to show tetrahedral nature. We can show the new iodine forward or back. I'm going to draw it forward. Okay? Or back. You get both. Because this is planar. Okay? It's planar like this. If the ICL is over here, the pi bond will attack forward and the bond will be forward. But if the ICL is back here, then the bond will attack back, or the electrons will attack back, and your bond will be back. But you got a 50-50 chance, because the molecules are all around 50-50. This is where the ICL was forward, and so the electrons had to come forward to bond to the iodine. This is going to back bond. When it back bonds, we're going to get our iodonium ion, right? But this is still forward. And the new bond here has to be forward. And now that's iodonium. Now importantly, this ethyl would be back. It has to be, because this is now tetrahedral. 2 in the plane. If that's forward, the other thing now has to be back. So we get to that point. Is this really an intermediate? No, NAF. This is not really formed. This arrow movement happens at the same exact time, and most books will actually just show it like this. They'll move that arrow all at once, never show this, and go directly here. I think it's too many arrows. You guys aren't able to follow it. I showed this. This is important anyway, because this is where the cation would form. And this is the same place that the nucleophile attacked. What's the nucleophile? Cl minus, which was formed right here. Electrons become Cl minus, 4 lone pairs. It's going to end up bonded here, the same place we would have had cation, but it's not really a cation. It's back bonded. And so it attacks here, but instead of attacking a free cation, it attacks and kicks off the leaving group. But this has stereochemistry built in here. How does this come in compared to the leaving group? It starts with a B.
Backside.
Yes, it's backside. Thus, this bond is still forward. Nothing happened to it. That iodine is now released. It's no longer bonded down here. This bond was forward. Okay? So this had to come in backside. So it came in back, opposite of forward. The ethyl actually gets pushed forward. Can you guys see in the back? This would be your outcome here. The iodine in Cl would be anti or trans. But you would also get an Antemer. and Antemer would be the mirror image. That's where all this is reversed. Backside. Gotta be careful about backside. It might be better for you guys to call it opposite side. Because sometimes backside may be from the front. Yeah, if the leaving group is pointing that way, then backside is referred to compared to the leaving group. Backside may be from the front if the leaving group is pointed back, because your backside has to come in this way and kick it off. But here the leaving group is pointing forward. These two bonds are on the ring this way. If I'm the ring, the two iodine bonds are coming forward. And so the chloride comes in towards my back and kicks that bond off, and this just opens up. And so the chlorine came in from back, and the iodine is like that. Okay, we'll do more of that going forward. What's the one on the bottom? Deuterium is an isotope of hydrogen. DCl. Deuterium is often used because it leads to stereochemical or stereochemistry, where if this was a hydrogen, you would not have as much stereochemistry. So you can give that one a try. Any questions about any of that? Also, you know you got to make progress. I know many of you are not where you need to be with mechanism. And so as I discuss stereochemistry, if you can't even follow mechanism, then you're getting more and more and more and more behind. All right? Question?
Can you show us how the ethyl just moves, you said? I mean, is it because of the rotation of the other bond?
It gets pushed forward. Let's demo with my high-quality demo materials here. Let's see here. We'll see if this works at all. The blue is a leaving group. Okay, let's turn it this way. Blue is a leaving group. This is an existing group. Bonding to the same carbon as the leaving group, right? The ethyl's bonding to the same carbon as the iodine there. Okay. The blue is a leaving group. Here's a nucleophile. It comes in backside, so it comes in here. And it's going to kick off the blue. So it comes in and it bonds and kicks off the blue. Okay. But as it does that, this is the group that's going to move. Right now, this group is this way. As it comes in, it pushes this off. This has to make room. This becomes emptied space. And if nothing changes, it will be a crooked bond angle. To achieve the 109.5, this moves to occupy that space that used to be here. So ultimately, the black is back. This comes in, kicks off the leaving group, but it pushes this forward. And so while this was initially back, it got pushed forward because a new thing came in, and things had to adjust. It comes in and it goes like this. Because right now the leaving group is in that space. This comes in, and we get the tetrahedral like that. And so this has been moved from back to forward.
Okay.
The alpha was back. It got moved forward whenever that group came in from the back. We'll do more of that. That's called inversion. You know, actually inversion is covered during test 3. Okay? But what I do is I tell you everything at once. Because I don't know how you would understand it otherwise. I could just show you this moving forward and never talk about it until test 3. I don't see why you wouldn't want to talk about it now. So, everything we're learning now builds, and when we get to test 3, you'll know what inversion means. Okay, we need to move ahead. Epoxides. Green sheet, next topic, epoxides. Including, if you look at our reactions, we're going around clockwise. The only thing I won't do is I won't call that inversion. I mentioned it, but test 3 will call that inversion. Because most all your mechanistic chemistry is all very similar. It all goes hand in hand. But where you guys get messed up is when you want to consider a million things in isolation and never see how it's very consistent. It's one really nice story if you learn it as a general approach. Once you start memorizing a million things, you never see the connections. Okay, epoxides. And epoxides are a 3-membered ring with 1 oxygen in the ring. Cyclopropane would be all carbons, 3 carbons. This has 1 oxygen, called an epoxide. Also is called an oxyrane, but most people call it epoxides. Epoxides are made from alkenes. You take this alkene, we can get this epoxide. Now, if you look at it, this used to be the alkene. And now we have an oxygen bonded to each of the alkene carbons. And that's it. So there's really no choice of where do you put the oxygen. It's bonded to both of the alkene carbons. There will be stereochemistry here, though. You do this with a reagent like this. This is condensed formula or structure. If this was a 2, that would look like a carboxylic acid head group. It's very similar. It's got an extra oxygen in there. It's called a peroxy acid. Because when you have oxygens bonded together, that's called a peroxide. Okay? Now, if this was an H over here, and if it was HOOH, well, that's hydrogen peroxide, like in your medicine cabinet. Here, one of the oxygen is bonded to this acyl group, and that looks like a carboxylic acid. It's called a peroxy acid. R group is general. There's a variety of R groups that are possible for these peroxy acids. One of the most common is where the R group is a benzene ring with a chlorine in the so-called meta position. Meta being a 1-3 relationship. And this is called metachloroperoxybenzoic acid. It's in your textbook. Most common peroxy acid. Now let's look at the peroxy acid. The 2 oxygens are bonded together. That's a lot like 2 bromines being bonded together. And this can become polarized, and one can become partial positive, one can become partial negative through polarization. All right? Now, oxygen is not as easily polarized, so it's hard to use something like this. That doesn't work as well. But when one of the oxygens is bonded to the carbonyl group, we have some polarization there, permanent polarization. Because this carbonyl is polarized towards the oxygen. Pi bonds are very polarizable, so it's very polar, leaving this partial plus, partial negative. But because of this partial plus, the electrons are pulled this way, and these electrons are pulled this way. All the electrons are pulled towards the carbonyl oxygen. I heard it. Some of you just said, why? I heard you. Well, keep asking. Like after class. If you want to know more, ask why. I can't explain every single thing. But right there, the polarization, that is very important. And we could talk about it for 15 more minutes, but we don't have time. It's polarized. Ultimately, in your peroxy acids, the end oxygen is partial plus. And the electrons attack the partial plus. The end oxygen is electrophilic. So this attacks, we got the electrons here, kicks off this oxygen just like we kicked off the bromine. This electron movement would give this carbocation. By the way, we didn't ask, where do you leave cation, left or right?
Left.
On the left. That's why I left it on the left. Right? No, left. Okay, do you think this is really going to form, or is something else going to happen at the same exact time? No, back. The new group has a lone pair. Whenever the new group has a lone pair, or in a minute something else, it's going to back bond. And if it back bonds, what do you get? Well, it's down below. Would you not then get this? Yes. By the way, we don't magically lose H's. Now, question. I showed two different steps. Do you think this is me just being me on the board, or is this really how it happens? What do you know about this? This is not actually formed. Anytime the back bonding happens, this actually happens at the same exact time. Okay? That is, again, some books will show it like this. This is back bonding at the same exact time. I think this is too much. And I suspect that if you understand this arrow now, it's only because I showed you this way first. This is concerted. This is the first intermediate. That's not an intermediate in this mechanism. That's just me drawing something on the board to help us along. Okay, I'm never going to explain that again because I've done it 4 or 5 times. Here's our first intermediate. Look how close we are to final product. What do we have to do to get to final product? It's got to lose the H from the oxygen. Well, right here, this got kicked off and became this. By the way, I know a number of you would not be able to show this being formed from this because you're not using your mechanism. But if you got this, what does this arrow mean? Bond is being broken. Electrons moving on to oxygen. 3 lone pairs. It's minus charge. That's what came from here. This minus can take the H. These electrons move here. We get the epoxide plus what? Plus this. So essentially, our starting peroxy acid loses an oxygen in the mechanism and becomes just a regular acid, carboxylic acid. And that's it. Now this looks a lot like the bromonium ion. Obviously this is oxygen. But the big difference is bromonium ion cannot go neutral by losing an H. It has no H to lose. So with the bromonium ion, you typically have a nucleophile come in, and this gets its electrons this way. Here we have an H we can lose, and it can get electrons by an acid-base reaction. And the ring remains intact, and that can be isolated as a final product. Typically, you do not isolate bromonium ions, although I did give you a reference where some have been isolated. Very analogous, right? Okay, this is called making an epoxide. Your reagent may be shown like that, generic peroxy acid. You may see MCPBA. You got to recognize reagents. And then at the end of the day, alkene reacts with peroxy acids to give epoxide. Let's show reaction here. MCPBA. What's this? Dichloromethane? What would its purpose be here, maybe? Solvent? Have anybody ever used dichloromethane as a solvent in lab? Yes. Sometimes solvents will be shown. You've got to learn to recognize solvents. And solvents, almost by definition, do not react. They're just here to dissolve things. But you've got to recognize them and get used to that. It's a solvent. Here's your peroxy acid. What's going to be the product here? There you go. Right? We now have the 3-membered ring epoxide. The oxygen's now bonded to the 2 carbons of the original alkene. You do have stereochemistry here. With talk about stereochemistry later. Basically, this propyl group can be drawn forward or back. But in terms of just getting everything connected to the right places, your connectivity, here's your product. How about down here with this ring? When we have rings, it's a little bit easier to show stereochemistry here at the outset. Question?
Do we need to show our lone pairs in the final product?
I mean, I'll let you get away without showing lone pairs, unless the question is show a Lewis structure. That sounds like a more formal question. But typically, a lot of people will not always show lone pairs, and you'll see lots of structures. I sent you a structure of the drug, the fentanyl, and I guarantee you none of my heteroatoms had lone pairs. Okay, well, let's look at this one. Rings are easier to show stereochemistry because it's fixed. Can you show product here? This is the type of thing where you got to work on and show it, and we'll look at it next time. Because if I just stand here for 30 seconds and then draw it, it does you no good. You need to sit down. The rest of these, let's show some precise stereochemistry. All right? What type of precise stereochemistry? What are the choices of the stereochemistry? For again, it's easy just to show the product without considering stereochemistry. Although it may look a little funny with the ring because it's actually now two rings. That used to be the alkene, right? Now you got a three-membered ring with the oxygen bonded to the two alkene carbons. Again, that's a 6 and that's a 3. But what's the stereochemistry here? Because both of these carbons are now tetrahedral. And also when you have two, now you have relative stereochemistry. So think about that. The first is, what are the possible choices? Because you have to first know the choices before you can decide amongst the choices. The ones down here. Whenever your alkene has two sort of prochiral carbons, which typically for us at this point is disubstituted, that was monosubstituted. This is going to have more stereochemistry. Again, yes, you're just going to connect these two to an oxygen. But what's going to be the stereochemistry here? These you really need to be looking at. But again, it's not, getting the right answer is just the second thing. The first thing is, what are the choices here? What stereochemistry is in play? That's what you need to be looking at here. All right? We'll come back and look at these a little bit later when you've had some time to do some work on those. So the synthesis of cyclopropanes. Another three-membered ring, but this one's with all carbon. Cyclopropane. Cyclopropanes can also be made from alkenes. Two different ways we'll look at. The first way is using diazomethane. Ultimately, we are going to make something called a carbene. A carbene. CH2 carbene. So the structure's drawn here. All right. Let's maybe look at it a little closer. This is a carbon with two hydrogens and a lone pair. There's a carbene. First off, is that a typical carbon? No. carbon, 4 bonds, no lone pair. Not a typical carbon. Does that carbon have a charge? What's the charge of this carbon? It's neutral. Now that's not what I suggested on day one. I said if it's not typical, it's going to be charged. Well, this is an exception to that. It's not typical, yet it's not charged. It's a neutral carbon. And this type of carbon is called what? Sorry. It's called a carbene. Sometimes called a divalent carbon because it's got divalent meaning 2 bonds. 2 bonded carbon with a lone pair, a carbene. Now, it's neutral, but a lot of people like to show 2 charges. Net neutral, but it's got dual character. For example, it's a carbon with a lone pair. And usually a carbon with a lone pair is usually a carbanion, that's usually minus. The lone pair gives it sort of nucleophilic character, and it's like it's got negative character because of that lone pair. But it's also got an empty orbital. What's the hybridization of this guy? Somebody? sp2, right? Okay. And it has an empty p orbital. You should all be able to graph that and see it's got an empty p orbital. But something with an empty orbital is going to be electrophilic. Question, does it have an octet? No, it does not. It only has 6 electrons in terms of octet count. Do you think that a carbon would like to have more electrons? Yes. It's thus electrophilic. And usually things that are electrophilic are positive. So it's also got some positive character. So showing the 2 charges, it reinforces the fact that it has dual character. Overall, it's net neutral. I like to show 2 charges because I think it helps you guys. That's why I show it. It also helps me remember it's got dual character. Okay, this can be formed from diazomethane. All right? Diazomethane. Diazo. 2 nitrogens. 2 nitrogens and methane, 1 carbon. 2 nitrogens and 1 carbon. This is the structure of diazomethane. It cannot be drawn without charges. It's net neutral. Now, diazomethane is actually an explosive gas. We won't be using it in lab. This is the structure. If you heat this thing, it will break apart. And if you don't do it right, it'll do it very fast, and it'll be very exothermic, and it'll go boom. But if you look at this structure, if these electrons move on to the nitrogen, what will that give? This will produce nitrogen gas. And it'll leave behind a divalent carbon with a lone pair. But this is your carbene. It comes from just heating this very gently. Control. All right? But your carbene is a reactive species. And the alkene reacts with it. The pi bond attacks the carbon. Let's see. Is it kicking anything off? No. What's it attacking? Well, you got to remember, it has an empty p orbital. These electrons are moving into that empty p orbital. A lot like if, could the pi electrons attack a carbocation? Yeah. We say that the electrons like positive, but if you get more into it, the electrons are adding to the empty p orbital. This has an empty orbital. Same thing here, it's got an empty orbital. These electrons make a bond to the carbon. It's sort of like bonding to the positive feature. All right? By the way, where are we going to make cation here, right or left? on the left. This is where I made it. So we just made this bond. The lone pair remains. By the way, this carbon is now minus. Where this carbon's neutral. Now minus. It has a lone pair. It's still there. What can the lone pair do? Boop. Back bond. You see that coming? Boop. And when it back bonds, what do you get? You're done. You don't even have to remove an H from the carbon like we had to with the epoxide. That's it. So, how many intermediates in this reaction? From the alkene to the product? No intermediate. That's not really formed. Can we do it again? Last time we were kind of too new at it. Here's the alkene. You're the carbene. All right? Oh, empty p orbital. These electrons are held a little loose. Pi bond, they're not held tight. Okay, I like p orbitals. Empty p orbitals. I like empty orbitals because I can go make a sigma bond. Okay, but guess what? You have a lone pair. So as soon as I start to move and go bond to you, as soon as I start to bond to you, this lone pair needs to be coming this way. All right, and you're going to bond here. I'm going to start moving. Boop. There we go. There's your product. There's never any intermediate. These two are concerted. And we get a cyclopropane. No intermediate. That's using diazomethane. You can also make carbenes using chloroform. This is sort of a specialized carbene because it's going to have two chlorines on it. Carbene-carbon has two chlorines. Your product is going to be a dichlorocyclopropane. This could be done in the lab. This is safer. This is chloroform. It's a common solvent, but here it's a reactant. Hydroxide, and we can get such a product. Carbene is formed over here by some standard acid-base chemistry. The hydrogen of chloroform is slightly acidic. Hydroxide can act as a base. Take the H. These electrons move on to carbon. That gives this plus water. It's just like we did 3 or 4 weeks ago. Why is this particularly has some acidity? Because this is somewhat stable. Why is this anion stable? Because it has 3 chlorines pulling, right? How do you stabilize an anion? You move electrons towards it or pull away? Pull away. This has 3 chlorines pulling and stabilizing this carbanion. That's why chloroform has some acidity. We can get to this point, okay? At this point, carbon's like, you know, I'm minus, but I would rather not be. One of the chlorines says, well, what if I just leave? So what if I just take my electrons and go? What will that lead to? First off, the chlorine will now become chloride when it takes the 4th lone pair. Carbon will only have 2 chlorines. It'll still have that lone pair, and it'll be that guy. But guess what? That's a dichlorocarbene. That's the same as above, except it's got 2 chlorines instead of 2 H's. Your dichlorocarbene can be made much more conveniently in lab through this acid-base chemistry. See, the chlorine left and it became minus, like chlorine loves being minus. And the carbon went from minus actually to neutral. Even though it's a weird-looking carbon, it's now back to neutral. So that's how this comes this way. And from here, you need to do your mechanism. This attacks the positive part of the carbene. Where are you going to leave cation? Over here. But guess what? Does that actually exist? No, that's just us drawing it on the paper. Because we know at the same time this lone pair is going to be back bonding, right? I could have just did it like this and never showed this. But that lone pair is back bonding the same time as this is. Okay, I'm just showing it separately. And when you back bond, well, that's it. You're done. You don't even have to remove a proton. So this is the idea of carbenes. These reactions require stereochemistry, just like on the previous page with the epoxides. Please be looking at these. The important thing here is you've got to form questions. That's the first step. The first step is not showing product. The first step is, what do I need to know here? What do I need to be looking at here? And what questions do I have about those things? Then once you get those questions answered, then you can show product. But you guys have to form the questions. Question?
I don't know how to phrase this question, but the reactants, how do we know that those two species are reacting prior to being added to the alkene? Do you understand what I'm saying? Because if they're
do we know these are reacting before this?
right, I mean those are added together in
Okay.
the flask and then added, because if not, then we would have had something different,
Well, okay,
right?
a couple of ways. First off, will an alkene just react with chloroform? And the answer is no. And we would have to, for the alkene to react, you've got to have some electrophilic species, and it will not react with chloroform. And it certainly will not react with hydroxide, because these are electrons. Electrons are not going to react with an anion. The electrons will react with a cation, like an H+. So eventually you got to know that the alkene is not going to react with these individually. So something has to be generated here for the alkene to react with. And here's the other thing. A lot of reactions you look at in organic chemistry, there is some memorization. People say you can't memorize in organic chemistry. I say phooey. The memorization helps get you going. For example, when you see chloroform hydroxide, and I want you to tell me this answer a year from now. Chloroform hydroxide, what reaction are you doing? You're reacting an alkene with a carbene. Because you'll never see chloroform and hydroxide together doing anything else in organic chemistry. So that's your starting point. Whenever you see a peroxy acid, what is it going to be doing? It's going to be converting an alkene to an epoxide. You've got to memorize that, because that's your starting point. You've got to know where to start. Okay? And most reactions we look at, many will have more variations. But that's another way. Whenever you see this, ding, 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 and again, this is something you put on a note card. And you say, on the back it says, hey, I'm doing a carbene reaction here, and I'm going to make a dichlorocarbene. But from there, your mechanistic knowledge kicks in. And your understanding of how do I generate the carbene. Okay, good. Cyclopropanes. They look very strange. They are strange. Ring string. Does that mean we can't make them? No, you can. We just showed how. And there's actually a lot of drugs that contain cyclopropanes. I mentioned this before, but here's some more. Okay. Singular. Ever heard of singular? I think so. Okay. Cipro. Yeah? All right. It's amazing how many. Carbenes. Any applications of carbenes? This is a drug, anxiolytic drug called Paxil. When it's metabolized in the body, a carbene is formed right here. That's a carbene. Carbon with two bonds and a lone pair. And so if you want to understand this discussion of the metabolism of this drug, understanding what a carbene is helps you read this. And okay. All right, oxymercuration. We're working around way around the dial there on our schemes there. Oxymercuration and then hydroboration. Actually, only two more to go on that big scheme there, on the green page. I think, though, maybe let's go back, because instead of getting into a new topic with only a few minutes left, let's do a couple of these. Let's do the one with the ring first. Again, rings are a little easier. Carbene, cyclopropane. All right, if we don't do any stereochemistry, we're going to have boom, 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 and boom. We'll make the dichlorocyclopropane across the pi bond right here. Yep. Everybody there? Questions?
Will H2O and KCl also be products of it?
Yes, if you want to fully balance that, it should be potassium chloride. Yes, because we generated a chloride there, and yeah, I mean there's a potassium up there. I didn't show a cation. I didn't show a cation, but whatever the cation there is with the hydroxide is going to sit with the Cl minus, and you could show KCl. If it's dissolved, it's ions, but you can still show it like that. Here we go. But what's the stereochemistry? Because these two carbons are now tetrahedral. Where there they were trigonoplanar. Question, how about these two bonds? Typically we show the ring all kind of flat in the plane, although we know it's really like a chair conformation. We've been there, right? But those bonds we're going to continue to show in the plane. The substituent bonds are what we usually show forward or back. How about these two bonds that are making the ring here? Are they going to be cis or trans? Cis? Anybody else? Why cis? Well, the easiest question is because they have to be. You can't make a premium ring trans. If I'm here, if one bond's here and one bond's here, how are these two going to bond together? And they can't. But if both are forward, now they can bond together and make a ring. All right? But let's really look at it. I wish it was flipped around so I could work it. We got the carbene here, right? Lone pair. Okay, there's charges here. Where are we going to leave cation, top or bottom? Bottom. So this pulls away from the bottom and attacks. I'm going to go this way. Boom, 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 boom. Now bonded up here to this carbon, but that's got to be forward or back. What do you want to do? Either. And a lone pair. And this is down here. And that's still trigonoplanar because it's a carbocation. Either up here. Now this back bonds, right? It's actually at the same exact time. We know that when it back bonds, it makes the bond down here. If this is forward, how is this new bond going to have to be? Here we go. Here's the cation. And the atom is forward. If this atom makes a bond to this, it's also got to be forward. Unless it's throwing a reverse curve. This thing is forward. Right? That's what that means. If it bonds down there, both bonds are going to be forward. And so that leads to Boom, 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 boom. They're both 4. And I'm going to draw that just as a line bond. Okay? But what do you want to draw this methyl now? It's actually going to get pushed. Because if it's planar, and this comes in and makes the carbon tetrahedral, that's going to get pushed and become tetrahedral. And this becomes like this. And let me finish this up. There's your stereochemistry, but you're also going to get an Antemer. The enantiomer is the mirror image. The enantiomer will look like, both of these will be back. That's a carbon and 2 chlorines. And this will be forward. That's the so-called mirror image. That's where everything's reversed. How do you get that? Well, you just do the opposite attack. Here, the reagent was in the front, and so this bond was in the front. But if your reagent's in the back, this would be dashed. And if that's going back and it attacks, how would the other bond be? Well, it would also have to be back, because if the attacking thing is in the back, the new bond has to be back. And that's going to push this forward. So you just get the reverse stereochemistry, and it leads to the enantiomer. Please look at the one up here, though. This is a touch more involved. And we'll be looking back at some of those. But next time we'll be looking at hydroboration, the boron reagent, and also the oxymercuration. I also sent you a handout for Wednesday. Stereochemistry. You need to start looking at that. Have a good day, guys.